Welcome! Today, we're going to pull back the curtain on 1D dynamic programming and uncover a really powerful secret pattern. We'll see how a single thread of logic connects some of the most classic coding interview problems you'll ever face, breaking them down into simple, manageable steps. Okay, so let's just dive right in. What if I told you that three problems that look completely different on the surface, one's about calculating numbers, another's about counting your steps, and a third is all about maximizing your loot? What if they're all actually the same problem in disguise? Yep, that's right. The problems we're talking about are Fibonacci, climbing stairs, and house robber. And here's the kicker. It turns out all three can be cracked using one single, elegant 1D dynamic programming pattern. To really understand this pattern, we have to go back to the beginning, its origin story, if you will. So let's build our foundation with a sequence pretty much everyone recognizes, Fibonacci. I'm sure you know this one. Each number is just the sum of the two that came right before it. We start with our fundamental building blocks, our base cases. F of 0 is 0, and f of 1 is 1. From there, every other number in the sequence just builds on that foundation. And this simple formula right here, this is the absolute heart of the pattern we're talking about today. The main idea is that the answer for any number n depends directly on the answers for the two steps that came right before it, n-1 and n-2. Now here's the really clever part. The smart way to do this isn't to store the whole sequence. All you ever really need are the last two numbers. So we use this slick rolling window technique. You have two variables, let's call them a and b, you add them up, and then you just slide that window forward. It's a brilliant trick that drops our space requirement down to constant, O of 1, which is a massive optimization. All right, so let's take this idea and move on to our next problem. We're going to see how this pattern starts to become really powerful when we look at something that, at first glance, seems totally unrelated, climbing stairs. So the question is pretty straightforward. You're climbing in stairs, and you can only take one or two steps at a time. So how many different ways can you get to the very top? Now, this sounds more like a counting problem than a number sequence problem, right? But is it really all that different? Well, let's think about it by working backward for a second. To land on that final top step, step n, what was your last move? You had to have come from one of only two places. Either you took a single step up from stair n-1, or you took a double step from stair n-2. There are literally no other ways to get there. And boom, there it is. That's the hidden connection. The total number of ways to get to step n is just the ways to get to n-1 plus the ways to get to n-2. Just look at that recurrence relation. It's identical to Fibonacci's. It's the exact same pattern, just wearing a different costume. But hold on, this part's super important. While the logic is the same, the starting points are different. For climbing stairs, we say ways of 0 is 1, because there's one way to be at the start, just by being there. This tiny difference in base cases is a classic interview pitfall, so you've got to pay close attention to those initial conditions. Okay, you ready for a twist? Let's take our pattern and add a really interesting new element. We're going to look at our final problem, the famous house robber, which introduces something new, making a choice. So picture this, you're a robber, and the rule is you can't hit two houses that are right next to each other. This rule forces you to make a decision at every single house. Do you skip the current house and just take whatever max cash you had from the last one? Or do you rob this house, which means you gotta add its value to whatever the best you did 2 houses ago was? And that whole decision process, well, it translates directly into this new recurrence relation. The best you can do at house I is the maximum of those two choices. See? We're not just adding the two previous results anymore. We're now actively picking the best of two possible paths. So let's break this down because this slide really clarifies how the pattern has evolved. For Fibonacci and climbing stairs, the main operation was just simple addition. But now with house robber, our operation has become a decision. We're using a max function. But notice the fundamental structure is still there. We're still relying on the results from 1 and 2 steps ago. That core idea hasn't changed at all. Okay, so now that we've seen this pattern pop up in 3 different forms, we can take a step back and boil it all down into a simple, reusable blueprint, one that you can apply to dozens of other problems. Here it is, your mental checklist, your game plan. First, you find that recurrence relation, how the big problem relates to its smaller parts. Second, you lock in your base cases, the simplest versions you can solve straight up. And third, you always hunt for the optimization. can you use those rolling variables to get your space down to a beautiful, constant O of 1. So why does mastering this one pattern matter so much? It's simple, really, because recognizing it and implementing it cleanly, that's a direct path to absolutely acing your technical interviews. And this table right here shows you exactly why. For all three of these problems, our pattern gives us the optimal solution: linear time and constant space. That O of M time, O of 1 space combo, that's the interview sweet spot. It shows you know how to write efficient, professional code. When an interviewer gives you a problem like this, they're really looking for three specific things. Can you clearly explain the recurrence relation? Can you get the base cases right? And finally, can you spot that key optimization to shrink the memory usage down to O of 1? And this is really the ultimate takeaway. Anyone can come up with a brute force recursive solution, but that's going to be exponentially slow. The optimized iterative approach, which is often called tabulation, is what really separates a good candidate from a great one. Hitting that sweet spot of linear time and constant space by building your solution from the ground up, that's what truly matters. So once you've truly mastered this pattern, you're ready to tackle even harder variations. Which leaves us with a final thought to chew on. You know how to solve this for houses on a straight line, but what would you do if the street was a circle?